Hey everybody, this is Professor Ross here, and we're talking about multi-digit multiplication in this video. We'd like to look at some models that you can use with students and also some strategies. So first, the models. If you were doing a problem like 25 times 18 with students, you could use counters with those students. How would this look? Well, 25 times 18 means one way we can think about it is 18 groups of 25 each. So we could lay out 25 counters, and then lay out 25 more counters, and then lay out 25 more counters, and then do that 18 times. Push them all in a big pile, a really big pile, and count them all up. As you can see, this is pretty tedious work. Hopefully, by the time you're into multi-digit multiplication with students, they don't have to rely on counters, but you can always bridge from counters on smaller numbers. Like we could do, 5 times 8, use counters, and then bridge towards better models like the base 10 model. Base 10 model is a little bit better because it's a lot faster to make 25, but basically it's the same strategy, right? Write 25, write 25, write 25, do that 18 times, count them all up, and you should get your answer. Now, an advantage is I can do this, I can draw a base 10 model a lot faster. Another advantage is that if students recognize something like, hey, if I got 25 there and 25 here, these 5 and these 5 add up to another stick of 10, and that's 50. And so I could just do 9 groups of 5 tens, and then it's actually pretty easy to just make your 10, and you can do tallies or sticks or whatever you want and get there a lot quicker. Probably one of the most important models for you to consider and for students to have time to explore and use is called the open array model. So an array, we could do an array. Actually, my counters here are already an array. They're a 5 by 5 array showing 25. An open array shows a rectangle that represents an array but doesn't fill in the specifics. So for example, this array would represent having 25 rows of 18 things each. And so we don't fill all those in an open array. And students kind of have the option to split this thing up in whatever ways are meaningful to them. For example, a student might look at this and say, well, 25, I could split that into, let me make this a little bit longer here, into 10 plus 10 plus 5. And then they might try to figure out how much would be in this 10 by 18, and they might be able to do 10 times 18 as 180, and that wouldn't be too bad. They might get down here and say, well, I don't know, 5 times 18, but we can split the other direction as well. Like 18, we could split into a 10 by 8, and so 5 by 10 is 50, and 5 by 8 is 40. And in the end, to find the total, we just add up 180 and 180 and 50 and 40, and that sum would give us the total of 25 by 18. As I said, there's lots of ways students can use arrays and split up arrays. So another student might look at this and go, hey, it's I'm going to split it this way, 10 and 8, and then they might know 10 times 25 is 250, and then they can get to work on 8 in meaningful ways to them. So those are open arrays, and a very valuable tool for students to use. Students will use different strategies to do multiplication as they explore problems like word problems or things like that. And these strategies can be useful and help students build understanding as we build up towards a more algorithmic approach. So some of the strategies include complete number strategies, partitioning strategies, and compensation. And these are ordered in complexity. The simplest to think about are complete number strategies. The most complex are compensation. Let's take a look at examples of each. And let's stick with the same 25 by 18. A complete number strategy says you're going to take all 18 groups of 25 and write them all out and add them all up. So you might have this giant column of 25, and you just add them all up and try and do it kind of manually, and it's a lot of work, right? It's kind of the parallel to using counters. You got to do a lot of work to get there. There are some kind of shortcuts students might get to, like they might do some partial sums along the way, like 25 plus 25 plus 25 plus 25 is 100, and then they start doing it in groups of 4, and get another 100, and so they might make their way there eventually that way. But at the heart of it is they've written down 25 18 times and they've added that all up. That's complete number. A partitioning strategy, on the other hand, uses some place value ideas to help students make sense of that. So for example, partitioning by tens and ones essentially says, let's take our 25 and split it up into 10 and 10 and 5. And I know that I've got 18 tens, and I've got 18 of those tens, and I've got 18 fives. And we can add these all up. And you might notice these sums turn out to be the same as the other ones we saw in the array. So there's some parallels to what students do with open arrays. And this would eventually give us the, is it 450? I think we've got here. The product of 25 times 18. And so that's partitioning by tens and ones. Partitioning by decades is similar, except that we don't have to split out into all the individual tens. So instead of saying 10 times 18, 10 times 18, and 5 times 18, some students are comfortable doing 20 times 18 and 5 times 18. So you can see this is a little bit more sophisticated strategy. They have to be comfortable doing a little bit more there, but it gets us to the same place. This might not look very different with this kind of problem, but let me just give another example. Let's say we were doing like 63 times 18. Partitioning by tens and ones would be 10 times 18, 10 times 18, 10 times 18. I got to do 6 of these. So you can see it gets a little bit tedious when we do it by tens and ones every single time, and then 3 times 18. Whereas a decade strategy would just be 60 times 18 and 3 times 18. So a little more sophisticated, but also a little more efficient when students can handle that. So some students might partition by decades. There's also partitioning the multiplier. And here, instead of partitioning up 25, we partition up 18, and we say I can do 25 times 10, and I can do 25 times 8, and get those products. And maybe this one they'd have to think about a little bit to get that, but it gets us to the same place as well. We add up those two parts. All of these have ways we can show them on the open array. I'd encourage you to try that out. See if you can make the open array and display those. The last and most sophisticated approach is compensation. And in compensation, we actually change one of the numbers. So if I'm doing 25 times 18, I might try a compensation strategy where I say 18 is kind of hard to multiply by, but 25 times 20 is not hard, right? That's 500. I can do that one pretty easily. But what did I do? I had 2 more 25s than I really wanted. This is 18 groups of 25, but I did 20 groups of 25. So I better take away, subtract 2 groups of 25, excuse me. Wrote that the wrong way. And that would be 50, and so I subtract those and I'm back down. I've compensated back for what I added in. We could also change the 25. We could go to 30 or down to 20 and compensate that way. Or you might say, hey, I can do 100 times 18. That's pretty easy, right? That's 1800, but that's 4 times too big. So I'll just divide by 4 and divide that by 4, and you'd end up in the same place. All right, so those are some different strategies students might use, and some of the models that students can use. It's great to have students explore interesting word problems and try the different strategies and see what other students use as you build toward a multiplication algorithm.